because of the curvature of the Earth, the distances between the towers of megastructure suspension bridges are further apart at their tops than at their bottoms, despite being precisely plumb lines straight up and down and 100% vertical. This would not be the case at all if the Earth was flat. This is due to the fact that we live on a planet, albeit an enormous one, and of course we are very tiny in comparison to it. Nonetheless, this is a fact. It is predictable, it is repeatable, it is calculable, and the calculations for what the variant of the distances would be is determined by a mathematical process that matches what we see in the real world. The computer program described in this documentation that predicts this is real-world applicable for future construction projects. This would not be the case at all if the Earth was flat, and the magical property that flat Earth people say replaces gravity should of course be universally going in the same direction down in parallel lines, which this proof shows is not the case. That is because all lines of pull for gravity all point down to a center of gravity that is a single point in the center of planet Earth. This is not an anomaly that happens on one or two bridges. It happens with all megastructure suspension bridges all over the world, and the computer calculations performed in the C++ program I wrote can be used to predict what the measurements would be for any future bridge because the math works with all existing megastructure suspension bridges. Before I get to the proof, I would like to say this introduction. This is the second mathematical proof that we live on a spinning ball that anyone can take and duplicate and prove in the real world that the mathematics work out in reality. As an introduction, I would like to preface a few things, so bear with me. I will make this as fast as possible before I delve into the details of the second proof that confirms the Earth is round. By the way, I also have in mind a third mathematical proof I could write, and I think that while I'm writing that one, I might come up with a fourth proof. Basically, after some time, I might be writing one proof after another. This predetermination of what exists in the real world is what people who are engineers tend to do who are faced with problems to solve. They work out the math using laws of physics or geodetic datum, and then they apply the math in real-world applications. And it works. The results match the expected results that they had worked out beforehand. People do this when they do things like set up broadcast antennas that they want to know its range. This is also the case in rocket science. Long before a rocket is rolled out to a runway, some software engineers work out the details of how the thing will work. They use data like the mass of the rocket, the amount of thrust required, and they use Newtonian laws of physics that depend on the Earth being a spheroid of a specific size and motion to make the rocket do what they want. And in the real world, if there was not some human flaw, the rocket does precisely what the math had predicted. So in a real sense, every time a rocket is launched, that is a confirmation and proof that the Earth is round. And they are launched all the time by many nations and many agencies all over the world, including Japan, Brazil, the European Space Agency, the National Aeronautics and Space Administration, the Jet Propulsion Laboratory, and even the Air Force. When I was a software developer in Silicon Valley, I once worked with another software developer who had once worked for NASA. Despite what the Flat Earth community likes to chant as one of their mantras, NASA does not lie. That is so highly improbable that one can say it is virtually impossible. NASA, as a government agency of a first world nation, has stringent bookkeeping practices. All the work is documented and accounted for. They have lots of checks and double checks, and everything is gone over with a fine-tooth comb. I have to briefly say one thing. I have made what I think is an important discovery as to why people think the Earth is flat. I tested this hypothesis out on a number of flat earthers, and my findings confirmed I was right. I think I know the core reason behind why people think the Earth is flat. After this video demonstration here is completed, I'm going to make a separate video on this topic. I think this is important, and I do not think anyone else has stumbled onto this. I've been challenged to show that my proofs have real-world applications. Well, of course, both of these proofs have real-world applications. The last proof calculated the difference in time of sunset between a view at ground level compared to a view from a high altitude above that location. There are multiple real-world applications for this. Some might even be life-saving. The time of sunset might be critical information for climbers on a high mountain. It might also have important business applications. Knowing when sunset occurs in a high-rise building means knowing when the power kicks in for night lighting or when the temperature will drop, or when scheduling when business meetings should conclude. And this current proof I will be discussing also has real-world applications. Large two-tower suspension bridges have some challenges in their construction because of their colossal size and because of Earth's surface is curved. These things are astronomically expensive, have to account for unimaginable weight and stress, and must be built to precise specifications. They cannot be off even a tiny fraction of an inch, or else over time they will wear and develop stress fractures and put lives at risk. They will collapse and die long before their time. After I first mentioned this suspension bridge proof to a flat earther, he scoffed and said that the small differences in the distances did not account for the 8-inch per mile squared rule. Well, it does. I've made a series of videos explaining what the 8-inch per mile squared rule really is and where it really comes from. Links to these videos will appear in the comment section of this video, and they are also in the documentation. And by the way, this is what the formula is in inches on a grid where it would be compared to a circle formula for the Earth. The same efforts to verify, validate, and quantify the 8-inch per mile squared rule are also applicable to the mathematics of this proof. They share the same stage, so to speak. The verification model of the 8-inch per mile squared rule also verifies the fact that the Earth is round using this proof regarding the nature of the towers of suspension bridges. They both work on the same planet under the same data for the same world. And now to discuss the proof. This graphic, representing a bridge on the Earth with its two towers pointing downward, gives us a glimpse of what we're dealing with and what challenges we are facing. This image is not to scale or proportion, of course, and is merely intended to introduce you to the challenge and the proof described here. The red lines on this graph represent the vectors on which the towers reside. These lines are plumb lines straight up and down, and as such they point to and intersect the center of gravity of the planet, the center of the Earth, which is represented here. The circumference of this Earth is represented here as a blue circle. Upon closer examination of this situation, we see a pattern which leads us to conceptualize how the mathematical solution will be resolved. Notice we see what appears to be a mirrored image of two triangles. Actually, there are two sets of overlapping triangles, but we'll get into that later. Just like the previous proof for the curvature of the Earth, this proof has a set of input values, a recipe of ingredients, so to speak, that we need to do our calculations on to produce the results we're looking for. Number one, we need to know the radius of the Earth at the location where the bridge stands. Just as we did in the last proof, we use this chart of the geodetic data to determine what this would be. Number two, we need to know the distance that the towers stand apart from each other at their base. If we refer to the graphic I presented to introduce the problem, where the circumference of the Earth is represented as a blue circle and the towers are presented as part of red vectors, you will see that the distance would be residing on the small blue line between the two red lines. Also, as I have suggested, we will be using half of this distance in our calculations, since what we are dealing with is back-to-back mirrored triangles. Number three, the third ingredient we need is the height of the towers. And those are the input values. Now let's return to some graphics to help us understand the problem we are solving. Let's focus on just one of the triangles we are working with, since eventually we're going to take the half distance we solve for and then double it to help us get our answer. To visualize our triangle, let's first have a look at it from the side, as we commonly do when we learned trigonometry in high school. What we're working with is a right triangle, of course. Let's first start with what our known values are before we solve for our unknown values. If you notice, these are actually two overlapping triangles which, fortunately, have the exact same angle. If we figure out what the angle is, this will help us figure out what the unknown values are. When I say we have two overlapping triangles, what I'm referring to as the smaller triangle is where the smallest side is half the distance at the base of the tower. Did I lose you, by the way, now? If so, rewind the video and rewatch the last few seconds, or go skim back in the documentation and reread where I describe the triangles and what make up the lines. The slightly larger triangle that overlaps this, or underlaps this, smaller triangle is where the smallest edge is half the distance of the length, measuring the distance between the tops of the towers. Now, all that I have described so far provides a foundation on which the solution is calculated. So now I will describe the logic within the C++ code to show how it is all done. After I get the latitude of the bridge, I use this geodetic chart to calculate the radius of the Earth as the location where the bridge stands. This is a commented out section of the actual code I wrote to test the program. It shows the various numbers I use for the radius depending on what bridge I was testing. Don't let the word double confuse you. This is a C++ term for the variable type used in the code. If I was to change this to actual English, it would look something like this. Next, we use this radius to calculate the circumference of the Earth that we will be using. Then we input the height and the base distance between the towers. For those of you who are not familiar with software design, development, and testing, let me explain something. This does not mean that I made calculations for all the bridges at the same time. No, what this means is I individually tested the code for each of these bridges at one time. When you comment out sections of code, you are deactivating it. So with each test, I would activate the code for one bridge by uncommenting out the code for that bridge and keep the code for all the other bridges commented out. And now to find out our angle as represented here. The fraction of the base distance, in other words the distance between the two towers measured at their base, over the circumference of the whole Earth, is the same as the degree that we're looking for divided over 360 degrees. Just as the case was with the previous proof, the purpose of this proof is not to instruct the reader or viewer on fundamental algebra and the rules employed to solve for fractions of equality. But the degree that we're looking for is solved by this one line of code in the program. We will use half of the angle since, as explained earlier, we are using two mirrored triangles, and the reason we are doing this is because fortunately these are right-angled triangles. And this means we can employ sine and cosine laws. We also have to convert the angles we use in our calculations into radians because the code unfortunately requires this for its sine function. Now we use the definition of the sine function to solve the problem. The angle is the same for all of the right 90-degree triangles denoted like this. A sine of an angle is also the same as the opposite length divided over the hypotenuse, as the comment section of the source code states. Now to solve for the distance between the tops of the towers using the hypotenuse of the larger triangle. Our hypotenuse is the radius of the Earth plus the height of the tower. That is our h in the, quote, sine of the angle equals O over h, unquote, also known as opposite side over the hypotenuse. So simply by multiplying both sides of the equation by h, which is an algebraic trick, gives us sine of the angle times h equals opposite, which is the value we are looking for. And then now that we have that number, we multiply it by 2 to double it. This gives us the distance of the tops of the towers. Then we subtract this result by the distance at the base of the tower to give us our final answer. I have tested this code with several suspension bridges, and the math works out with reality, thus confirming that this is an actual proof that the Earth is round. One test I performed was for the Golden Gate Bridge. The Golden Gate Bridge stands at 37.8199 degrees north and 122.4783 degrees west. According to the geodetic chart, the Earth's radius at this location is 6,370,008 meters. The tower height is 227 meters. The length of the distance between the towers at the base is 1,280 meters. When I crunched the numbers by running the program, the measured distance between the tops of the towers worked out to be 1,280.0456 meters. This means that the difference between the tops of the towers compared to the distance between the bottom of the towers is 4.56 centimeters. I've been told that the difference of distance between the towers of the Golden Gate Bridge is just under 2 inches. 2 inches is 5.08 centimeters. So this program that depends on the curvature of the Earth for its calculations proves that the Earth is round because the results match reality. For completeness' sake, I've included in the documentation more bridge results that match reality, as I've also put in the comment sections of the code. And so there you have it. I will post this video online. In the comment section I will tell where to find the documentation as well as the source code for you to run this program for yourself. This concludes the second proof that the Earth is not flat. and is in fact a ball. There'll be follow-up videos to this presentation to come, but as it stands, this meets the challenge of producing two mathematically verifiable and repeatable proofs that the Earth is round.